Hello, and welcome to the E3SM data regridding tutorial. My name is Tony Bartoletti, and I will be providing this walkthrough of the regridding guide written substantially by Sterling Baldwin. A copy of this guide should become available to you at the following URL. That would be highlighted here, e3sm.org/resources/documentation/how-to/regridding in good time. I will begin by discussing some topics common to anyone who might be using these tools, such as the required execution environment, the map files employed by the regridding operations, and offer a few words about regridding in general. I will also briefly survey my workspace to demonstrate a layout that allows me to minimize clutter as I conduct the tutorial and to familiarize you with that environment. Then, finally, depending upon which version of this tutorial you may be viewing, we will exercise regridding examples with either atmospheric, land, or the MPAS ocean data. So let's get started. I will come here to the PDF regridding guide on my left and scroll down to Chapter 1. And we talk about the environment setup. As the guide explains, you should first establish an Anaconda environment in which the necessary NCO tools are installed. If you already have a Conda environment you wish to use, you may add the NCO suite of tools with the first command indicated here under Conda. That would be Conda install -c Conda forge NCO. If instead you would like to create a Conda environment that's specific to doing the regridding and only contains the NCO tool suite, the second command should work for you. And as you see, it names a environment called regrid, and I've used that one myself, and that's why if you look at my console window, my command prompt begins with the word regrid. There are also precompiled NCO tools available if you want to go that route. And the URL is up here under the NCO documentation. So at this point, I'd like to talk about regridding in general. Why do we do regridding in the first place? Turns out that, of course, many simulation models exist, and they produce data on different grid types and with different resolutions. In order to conduct side-by-side comparison between simulations or to combine simulation data in conducting forms of secondary analysis, the output must be presented on the same grid. If you have data on two different grids, you will need to convert the data of one into the grid of the other in order to compare or combine them. There are many regridding methods, but the most common are the area averaged and the bilinear methods, which I will describe briefly here. The area averaged method is employed when you are moving from a high resolution grid, the destination, or the source grid here indicated in red, and you want to convert the data into a lower resolution destination grid with larger cells indicated in blue here. The value that you're going to want to obtain for each blue cell is going to come from a variety of smaller source cells, and it will be the cells that are covered by the blue cell, either entirely or in some portion. And the contribution of the source cells corresponds to the fraction of those cells that are covered. So we see here that there will be 4 cells, source cells, that will contribute 100% of their value, or along the periphery we see that there are other source cells that will only contribute a smaller weight of their value, and that weighted average is what is assigned to the destination cell. In contrast, when moving from a coarse resolution, large cells, in this case the red source grid, to a grid that's of finer resolution, the blue destination grid, we consider that each source grid cell, imagine its values to be concentrated at its center, represented by its center point. And then every blue cell that happens to find these four cells, source cells, to be the closest ones, will have its center fall within the bounding box connecting the centers of the source cells. And that each blue cell then is going to receive some value from the four source cells, but in proportion corresponding to how close the center of the blue cell is to those red centers. So we can see in this case that the point P at the center of this destination blue cell will be receiving more weight from the value in this large red cell B than and the least from this one over C over at this end, which is further away. So that is pretty much what I'm going to describe about regridding methods. Now, because there exists a wealth of standard Earth-spanning grids already, regridding is facilitated by map files that are pre-configured to conduct the cell-by-cell weighting of cell contribution from a known grid, source grid, to a known destination grid. These map files are available at this Argonne National Laboratory site. There are scores of them. We won't have to pull those down because I've already got several of them on hand. As you can see here in my console window, there are scores of different source to destination grid transformations that are already available. We will only be using a few of these, of course, in the tutorial. So I might also add that the data that you might want to examine or regrid, there is a wealth of that data, E3SM data published, a wealth of climate model simulation data available at the ESGF ESGF node website here, with a search front end that will allow you to select data sets from different experiments according to a variety of different criteria. I've already downloaded and have available a variety of data that we'll be using for some regridding here. So before I go any further, I'd like to introduce my environment. You see, in my environment is divided into a variety of source directories that are already populated with data for these tutorials, and I will demonstrate these by just looking at a few files from each one. See, we have two directories of atmospheric model data, two of land model data, and two directories of the MPAS ocean data. And you'll be seeing some of that data depending on which video you may be viewing here. So likewise, once the regridding occurs, the output will end up in these different destination directories at the top. There, we can see that they're actually empty by replacing source with dest here. And there's nothing in these directories yet, but they will be populated as the example grid runs occur. So with that, I think it's probably time to launch into the actual regridding examples. All right, so for this version of the tutorial, we will be examining MPAS regridding, specifically MPAS ocean files. The guide is on my left. There's only 2 examples given here, but we will be running 4 of them. I want to include climatology and selected variable regridding. And on the right is my console. The data will come from these last 2 directories. You see them at the bottom of the screen. One is only for the year 1850. The other has all of the years from 1850 through 2014. If we take a quick look at the MPAS ocean files, that's what they look like. And you'll see that there's one for each month. And this pattern will look very familiar because, unfortunately, a lot of the regridding operations output files that are exactly the same name as the input file. So you can clobber yourself if you're not very careful. That is why I've taken care to write my output directories, if you see them up here, such that they describe exactly what I've accomplished in doing the regridding. That way you can tell. By looking at the file names, you cannot tell what has happened. So you got to be very careful about naming. That's one of the reasons why I've written my own scripts and did not want to rely on the the input and output directories that were given in the guide itself. So let's go ahead and take a look at the scripts that we'll be running. Sorry about that. These are all the ones that begin with C. And so these are, the first script will do a regridding of the entire year 1850, all variables. The second script will select only certain variables, again for 1850. The third script will do a climatology, wrap up by month, season, and year for the full 165 years from 1850 through 2014. And the last is a time series for selected variables, again, for all 165 years. So let's take a look at the first script. The initial scripts are relatively simple, and they all have a common format. You need to name the map file that you'll be using. This map file happens to be one that takes the MPAS native form, which happens to be EC60 to 30V3. I don't know what that means, but I think it may be some kind of a hex variable hexagonal grid. And what we're moving to is 180 by 360. That's 180 degrees of latitude, 360 degrees of longitude. So it basically divides the Earth into 1 degree by 1 degree little cells. So and so it's going to map from one to the other. You've got to name your input directory, where the files are coming from, and the output directory, where they're going. So we've already covered that part. Then there's flags that are required. This one, dash PRC type equals MPAS, simply explains that this is an MPAS regridding we're doing. And then the flag here at the end, --D2F, reduces the the variable values from double precision down to single precision, which has been determined to be more than sufficient for this type of work. And so then the command line will simply be nc remap, the utility, followed by the flags and the values for those different inputs, map file, input and output directory, and the other flags. So let's go ahead and run that. Doesn't take very long. You'll see that it's actually often doing more than one file at a time because it's running with multiple cores. So sometimes the output looks a little bit strange as it's generating it. I won't wait for it because it takes probably most of a minute. So I'm going to pause the recording and rejoin it as it's done.
This conference will now be recorded.
All right, that took a lot longer than expected. I think it took almost 5 minutes, a lot longer than the corresponding regridding that we did for the Atmos and land regridding in other tutorials. I think that's owing to the complexity of the MPAS hexagonal grid. It's a more sophisticated regridding. So now our files should be available in the output directory, dest, MPAS, ocean, 18360. So let's take a quick look at those. And there they are. You'll notice that if I compare them to the input directory, other than the fact that the input directory are links, the file names are identical. So if you happen to put them into the same directory, you clobber your files. So that's the reason I use specially named output directories. Now let's go on to the next example. This is actually no different than the first example with one exception, and that is this line, bars. Instead of regridding all of the variables that exist in the model, we're selecting a subset of variables. Okay, and it has to be a comma-separated list, no white space, and each variable that you've selected has to have both a time component and an end cells attribute. In other words, it has to vary over time as the years progress, and it also has to have a value specific to each grid cell. So other than that, there's no difference. The command line, simply we add -v and the var list that we've given. And so we can go ahead and run that. I think you'll notice in this case, I hope, it runs considerably faster. It's all done. That took about 10 seconds, perhaps. And if we look in the output directory, the files are there. Once again, they look just like the other file names. So how do we know anything's actually happened? It turns out that the only easy way to tell is to bring up another window here. I know this font is too small for you to see, but I think you'll still be able to appreciate the difference here. If I do a long listing of our first output, I do a long listing of our second output, the one with the selected variables, you'll notice that it is smaller by a factor of over 100 almost by a factor of 1,000, maybe 700 times smaller, since it's only regridding a selected number of variables. So each file here is just a little bit over 1 megabyte in size, whereas here it was 778 megabytes per file. So obviously, if you're only interested in certain variables, don't regrid the whole file, all the variables in the model. Select the ones you want. It'll run much faster and take up less space. So I think that that finishes the simple regridding. Now let's move on to climatology. So the script. The climatology and the time series both are similar, and they're considerably more complex scripts than the first ones we've run. In this case, really the additional complexity is simply that there's more parameters. There is at the beginning the very same material. You have a map file, same input directory. Well, in this case, we're using all of the years. Output directory, specific name, and we're looking at the same two variables. But in addition, you can now specify the start and end year of your, in this case, climatology. You can, you have to give a model type for the climatologies. In this case, MPAS Ocean will specify for the regridding and the climatology what type of data we're looking at. You can leave that off if it's atmospheric data. The default is CAM, the atmosphere model. We have the flags that indicate our formatting of the output, deflation, and you need to give a case ID. That case ID is simply the file name up to the variable part that has the changing dates. And there's also a flag called December mode. It turns out that climatologists like to think of the seasons as with winter being December, January, February, and then March, April, May for the next season, etc. The fact is, though, our files are year by year and go from January to December. So if we don't have if we're going to begin in the year 1850 and we don't have a December 1849 file to begin with, it will complain and give up if you don't specify this flag which says seasonally discontinuous December, meaning that you can ignore the fact that there's no initial December file. So other than these flags, there is again the command line. In this case, we're using a different tool. We'll use this tool both for the climatology and for the time series generation. It's NC-Climo, and simply followed by the set of flags that we've specified, whose values we've specified above. So we can go ahead and run that script. It begins by being a little bit verbose about the job it intends to do. This may take a little bit of a while. Well, maybe not too long. What it will do is generate for all of the years from 1850 through 2014 what each January looks like, what the history of February's, March, April, May. So it's doing a roll-up for each month of the year. And then it will do a similar roll-up for each of the 4 seasons. And then finally an annual roll-up. So there are the seasons. There's a lot of other output. and it took 51 seconds. Looks like it's not too bad. So now let's take a look at the output. That would be the dest MPAS 18360 Climo directory. And what you'll notice is for each of those different time units, each month, each season, and the annual, 3 files are output. The first file is the one with the long name, is the regridded. I'll come down here, it's easier to see maybe. It's the regridded Climo. So it's the climatology expressed in the gridded, the new grid, the 18360. But it also will generate the climatology on the native grid. That's the one with the short name. And then it adds a soft link name, and that points to the long name. So and so you can see here that we've got files for each of the months: January, the roll-up of February, all of these from 1850 through 2014. And so each month through December, then we have December, January, February, March, April, May, June, July, August, September, October, November, and the annual roll-up. So there's not much more to say about that. For our last example, we will be doing a time series for the selected variables. So let's take a look at that script. This looks superficially a lot like the Climo. There's 2 important things that make it different. One is that there is this additional flag, years per file. As it does the time series for each variable, it will roll it up in so many years at a time. In this case, for each output file, we're going to look at 50 years worth of roll-up. So it'll be 1850 to 1899, and then 1900 to 1949, etc. So there's that one addition. In fact, that is apparently the trigger that tells the NC Climo utility that this is a time series. In addition, you can work on the Climo. We said we needed a variable to tell us what the model was, -M, MPAS or CAM or CLM2 for land. You cannot include that. It will confuse the tool, I believe. At least it did for me. So we basically replace it with this one flag. Everything else is the same. We have our map file. We have our input and output directories, the variables that we're going to conduct for a time series, and start and end year. Same format and deflation. The deflation flags basically are variable by variable compression, and again the double to single precision conversion, and the case ID. So let's go ahead and run. Well, we're not going to actually run this one because it takes like 30 minutes or so. So I've already got the output present here, and it's in this directory. So we'll take a quick look at that. Oh, wrong one. Time series. That's the one I want. Okay, that's sort of ugly to look at. Let's make that a short listing. All right, so we can see that for each variable, in this case, the first one is the time monthly average pressure adjusted SSH. We have it run from 1850 through 1899. That's the first 50 years. And again, the time series is output both on the new grid and the native grid in the second file here. And then we do the same thing for the years 1900 to 1949, for 1950 to 1999. And then finally, there's not 50 years, but only 15 available to do the last file. And then we do the very same thing for the other variable, which is time monthly average SSH. And so that is the expected output for a time series. So that actually covers the material we have. The only thing I think I will close with here is give you another look at those notes I wrote earlier. So in case you want to write any of this down, you won't have to search back through the video to find them. So we have the documentation, the packages, map files, the tools, and where we can get this data if you want to explore it. And with that, I hope you enjoyed the tutorial and it was helpful, and have a good evening.